Okay, so in this review, we're really talking a lot about volume, right? Revolving a volume, or finding the area between two curves, or the volume rotated around an axis of some sort. So let's just jump in here and see what we got. Find the area of the region enclosed between the two functions. Okay, so it'd be really kind of nice if you knew what these functions look like, wouldn't it? Yeah. Because then we can see which one is above the other one on the interval from -2 to 2. So here's our graph. We have a cubic and we have a quadratic, right? We know some things. We know at least it crosses at +10 and this one crosses at -10. So we can make some assumptions probably about these things. That chances are, right, maybe your quadratic looks like this. I don't know, when it crosses at -10. And your cubic, let's see, maybe the cubic looks like this. So my assumption is that the cubic is going to be above the quadratic, right? And of course we can put this into a calculator if you would and look at that. It's going to look a lot better than my graph did. That looks pretty ugly, I must say. Okay, so we're going to assume that the x cubed is above the x squared. Okay, verify this on a calculator. In fact, I'm about to do that right now. There, verified. Yes, x cubed is indeed on top. Okay, and it definitely doesn't intersect in these points, so my graph is terrible. But, right, the point is that we're taking the integral from -2 to 2. Right, this is how we find the area of our function. We take the integral from -2 to 2, and it's the top function, which is x cubed minus 2x squared plus 10, minus the bottom function of 3x squared plus 4x minus 10 dx. Okay, so when we're finding the area between two curves, we're looking for, of course, their points of intersection. So we're just going from -2 to 2, whether they intersect there or not. Okay, I believe they do probably intersect at -2 and +2. So make sure that you can do this without a calculator. So I'm going to pause and simplify it real quick, and then we'll come back and finish. Okay, so we would do this work. Right here is your work when we're subtracting these polynomials, taking the antiderivative of that polynomial, and my calculator, which I ultimately looked at, told me the answer was 160/3, which you can't really see if it's in yellow. So 160 divided by 3 is the area between those two curves. Okay, so that's what we're looking for in these problems, is which function is above the other function and what is the interval that we're looking for. Okay, so we're going to do the same thing with this one. Okay, after some close examination, we find that the red function, okay, it looks really funky, like a little, I don't know what this is, but that's what it is. That's the graph. It's only available from -1 to +1. So on the interval from -1 to 0, the y graph is above the x graph. So this is your sign. I guess the red one is above the blue one. I made them different colors. So y minus x dx for one interval from -1 to 0, and then from 0 to 1, the sine graph is above your root graph. So it's the one above minus the one below. Okay, that's what you need to remember for the calculus, is that when we're doing these areas on an interval, it's the top function minus the bottom function. Okay, and we would put this into a calculator and it would tell us the answer, which we're not going to do at this moment. But you can, of course, always do that. So let's set up these ones. And it says sketch the graph because we really want to know which one is above and which one is below. So all of these problems, you need to know which one is closer to your axis of symmetry and which one is farther away. So we're going to make our graphs here. We're going to call f of x, we'll graph f of x in blue. So x squared plus 2 has a y-intercept of +2 and a normal quadratic growth of 1/1 up, 2/4 up. Okay, so this is your standard quadratic graph. Nothing strange about it. So here is x squared plus 2. And then we have our g, which crosses at +4 and goes over 1, down 1, and right 1, down 1, and right 2, down 4. Okay, so these are two quadratics that have nice points of intersection. So they intersect at -1 and +1, and we're rotating it around the x-axis. So this is the area that we're rotating. Okay, so when we're doing this, we need to think about volume. These are always circles when we're rotating. So pi times the integral from -1 to +1, that's the points of intersection. Right, you can find them by setting your two equations equal to each other and solving, and that's what you would get, -1 and +1. And we need to think about the radiuses here. So if we're rotating around the x-axis, this is your axis of rotation. Okay, the point 0. So which of these two functions is farther away from that point of rotation? Okay, the red one. So this is your first radius. So that's the g function, which is 4 minus x squared, right, because it's pi r squared. All of our circles have a squared radius. And in this case, the radius is given to us by 4 minus x squared, minus the closer one. So here's your second radius, which is your blue graph, or x squared plus 2 squared. Okay, now these are both quadratics, and we can expand them out. That's what we would do if you were going to do this by hand. I believe a lot of things would cancel out, right? The x to the fourths would cancel. Maybe your x squareds would cancel, and we get a fairly decent answer. Right, so be sure that you're able to do this type of a polynomial antiderivative in your head, but we're going to use our calculator, so we'll be right back. My calculator says 16 pi. So remember, the important thing is setting up these things. So we have to think about, right, what are the points of intersection? Right, what are your intervals? So your intervals are where they intersect. And then which function is farther from your axis of rotation? Okay, it's the farther radius squared minus the closer radius squared. Okay, so let's take a look at our next one. We're rotating this one along the line y equals -3. Okay, so it's a very similar problem, so we're not going to do all of it. Okay, now we're looking at y equals -3. All right, so then the function, I guess we should graph this in red again. This is your x squared, your 4 minus x squared function. Okay, so this one's radius is now the 4 minus x squared minus -3. Right, so we are adding 3 extra units to our radius that we didn't have before. Okay, the reason we didn't do it before is because we had, of course, 0 as your axis of symmetry, and -0 really doesn't matter. But when you have a thing other than 0 as your axis of rotation, you need to account for that distance in your graph. Okay, so this one would be similar. This would be the x squared plus 2 minus -3. Okay, and of course, minus a minus is a plus dx. Okay, so when we're rotating around something other than the origin, you have to keep that into account in your equation. Right? It's always minus that value. Okay, in this case, minus a minus adds length, but not always. So here's your second radius where we added 3 extra units to your radius. Okay, so number 5 is similar in nature. So let's just set up number 5. We have f of x equals 9 minus x squared, okay, which crosses at +9 as a -3 and +3y intercept. So there's our graph. And the line y equals 12 on the interval from 0 to 3. Okay, so we're not even looking at anything over here. We're just looking at 0 to 3. Okay, so this is the interval we are rotating, or this is the area, rather, we're rotating that stuff right there. Okay, so the line y equals 12. Okay, so we're rotating it this way, right, where 12 is your axis of rotation. Okay, so we have two integrals, right? So the first one is this length from here, right? Your first radius is simply 12, right? That's the first radius, minus your second radius, which is given to us by the graph of 9 minus x squared minus 12. Okay, so when we're rotating around a line other than 0, we have to account for that line in your equation. Okay, and it's from 0 to 3, they told us, if you did y equals 12. And then if you did 15, right, we'd be adding more to this, so we'd have different radiuses when we did change our different line, right? We'd move it 3 up, so we'd have to add 15 to our different lengths there. Okay, so make sure that you are adding, right? This is 0 minus negative 12. 0 minus 12 is the first radius. That would give us a cylinder, and then we have to subtract off this much here. Okay, that would give us the shape that we're looking for. Okay, so let's see what else we got. And of course, your calculator will tell you all these answers. I'm really just concerned about you setting this up. Okay, same graph, 9 minus x squared. Now we're going about the axis x equals 2. About the vertical axis, x equals negative 2. Okay, so let's graph it once again. We have the interval from 0 to 3. So that's 9 at the top, and positive 3 is here. So this is the area that we're rotating. And it's the line x equals negative 2. Okay, so we have a horizontal rotation, right? We are trying to rotate it this direction. A horizontal rotation. So whenever we're doing a horizontal rotation, we need to have everything in terms of y. Okay, we need to have a y interval for your height, right? The y interval for your limits of integration. And we also need to solve this equation for x. So we can have a y equals, or a y equation underneath your, underneath, after your interval. So in this case, we would have an interval from 0 to 9, right? That's our y's from 0 to 9. And let's see, the furthest radius away, right? The furthest radius away is our function solved for y. So let's solve this equation for x. Y equals 9 minus x squared. So x squared equals 9 minus y. Right, we add the x squared over there and subtract the y. And then take the square root. Okay, and since we're only concerned with the positive part of our graph, we're only concerned with the positive part of our square root function. So positive 9 minus y squared minus negative 2, right? And that adds in that extra 2 units here for the radius, which of course becomes a plus. Okay? So that's your first radius. Now don't forget about your second radius, the stuff down the middle that's getting subtracted. Okay, so minus, I guess this is 0 minus negative 2 squared. Right, because this other radius is the line x equals 0. Okay. Dx. I guess, no, dy, because everything needs to be in terms of y. So when we have a horizontal rotation, okay, and we had some of this in the other video about the circuit. When you have a horizontal rotation, all of your stuff needs to be y's. Y intervals, equations with y in them, not x's, and we're taking dy rather than a dx, because the widths of our circles are y values, dy. Okay, so when we're rotating around the y-axis, or a vertical or horizontal rotation, you need everything to be in terms of y. So let's look at 7. That gives us the same kind of thing. 7x equals root y, and x equals 0. So x equals 0 is this line. And x equals root of y. So let's see, when y is 1, the square root of 1 is 1. When y is 4, the square root of 4 is 2. And we're rotating around the y-axis. Oh, good. We don't have to do any other radiuses here. Okay? So once again, we have a horizontal axis rotation. Right, we're rotating it this direction. So a horizontal axis rotation, all of your integrals are going to be in terms of y. So we have a 0 to 4. Sorry, not 0 to 4. It said start at 1. So we're just rotating this much. We're not going to have a round tip. We're going to have a flat one. So 0, sorry, not 0, but 1, 1 to 4. So our interval is from 1 to 4. Okay, this is already solved for y, so that's just root y. And I believe we are squaring it, right? So pi radius square. Sorry, we need a pi in front of that one up here also. And we probably need a pi in front of this one. Everything here that we're rotating needs a pi. Oh, I forgot all the pi's. Okay, so sorry. When we're rotating in regular circles, it's pi r squares. Pi's on the outside. dy. Okay, and I believe that's really all we need to do, except for stuff it in the calculator. Okay, so how about this one? Here we have x equals y squared. X equals root y, rotated about the y-axis from 0 to 1. Okay, so we just did x equals root y. That one was pretty okay. So there's 1 and here's 4. Oh, we just want 0 to 1. Okay, never mind. We don't need that point. And let's see, if x equals 1 squared, that must look like this. So this is your little leaf graph right here. Tiny little leaf graph. Rotated around the y-axis. So there's your axis of rotation. So we're going to have this same little leaf on this side and have a nice, I don't know, whatever it's going to look like. But it'll be over there. Okay, integral from 0 to 1. Pi. The farther radius, right, which one of these is the farther equation from your line? X equals 0. It looks to me like it's this one, which is root y squared minus the closer radius, which looks like it's y squared, dy. So when we have two functions rotated around a central axis, it's the farther radius minus the closer radius. Okay, make sure we're always multiplying these things by pi outside of your integral to give you your circle. Okay? So there's page 1.